the recording also. Right, so we'll finish off the doubts of vectors, then we'll start with the next chapter after that. So exercise 4, question number 2, let's start with this. So it says that f is given by the equation q into v cross b. And in each of these, we have to find out the direction of f. What will be the direction of f in each of the situations given? So in case 1, q is positive. Okay. So if q is positive, that means that f is along the vector v cross b. So see, what you're doing is, when you look at the quantity f, it is a scalar quantity q multiplied by a vector quantity v cross b. See, this quantity here, it's a vector, and this quantity here, this is a scalar. So if that scalar quantity is positive, that means the left hand side is parallel to v cross b. If it is negative, then it would have been opposite or anti-parallel. Is this point clear to all of you people? Right. So now, for example, in one of the options, it's shown to you that in terms of a coordinate frame, it's like this. For example, in the xy plane, I'll come to it, but okay, first understand this, okay? And suppose this is the z-axis. Now, in case C, for example, in part C, it is shown to you that, or part 3, whatever, it is shown to you that your B vector is along the z-axis. And your velocity vector is along the x-axis. Sorry, along the negative y-axis. The velocity vector is like this. Okay. So that means B is along minus j cap and B is along plus k cap. Okay. And Q is positive because we are doing case 1. So force is along which direction? B cross B. So that means it is along minus of j cap cross product with k cap. Yeah. So j cross k is what? I. So minus of j cross this thing becomes how much? It becomes minus I cap. So the force will become along minus I cap or negative x axis. Okay. Which you can do by right hand thumb rule also. If you point your thumb along this V and your fingers along V, you will see that your palm is pushing in this direction. It's pushing in the negative x direction. This will become the direction of force. Okay. But on the other hand, you also know that suppose you had Q as a negative point and F is equal to Q into V cross B. So that means F is equal to a negative scalar multiplied with V cross B. तो इस केस में क्या हो जाएगा? F will become opposite or anti-parallel V cross B. So now suppose you have a case like this where Let's take the case 1, where in the XYZ plane, your V is shown to be along negative x-axis and your B is shown to be along positive y-axis. So here V cross B will be in which direction? If we use right hand palm rule, B cross B will be in this direction. But here the force will be opposite to that. So the force will come out to be in which direction? The force will come out to be in this direction. Or you can understand it this way. V is along minus I cap. B is along plus J cap. Therefore, V cross B is along minus of I cross J. So that becomes minus J cap. Now, F is Q into V cross B, where this is negative now. Therefore, F is opposite V cross B. Therefore, F is along plus K cap or positive Z axis. Okay, is it clear, people? Let's minimize this a little bit so that you can see the whole thing. And okay, so we'll take down these two parts and similarly work it out for the others also. So Q अगर negative होगा तो F का direction कैसे होगा? It will be opposite to V cross. Okay, good, Shikhar. So we'll come back to exercise 4. But in the meantime, there's also a doubt from exercise 2. So I'll switch back to that and then come back to exercise 4. Okay. So now just take a look at this question, all of you. Exercise number 2, question 3. Is there a doubt asked by Shravani? So we'll just discuss this question. Just take a look at the question, all of you first. Okay, so the question is like this. It says that V1 vector plus V2 vector, the vector sum of V1 plus V2 is perpendicular to the vector V1 minus V2. And from this we have to now check all the options which are given. So option E says it means that V1 is perpendicular to V2. Option B says that it means V1 vector's magnitude is equal to V2 vector magnitude. Option C says that they could be at any angle. So it says that V1 is null vector. And D says that angle could be anything. Angle between V1 and V2 could be any value. So you have to check all these options. So let's understand what this means. V1 plus V2 is perpendicular to V1 minus V2. One way to interpret this is that their dot product should be 0. So this will indicate that V1 square minus V2 square will be 0 when you open the dot product. So it means that V1 is equal to V2 in magnitude. So that means obviously this option is correct, this option is wrong, because there's no necessity for them to be perpendicular. And definitely we don't want V1 to become null, because then they would be opposite vectors. If V1 was a null vector, then V1 plus V2 is plus V2 and V1 minus V2 is minus V2. So now let's pay attention to this, why this one is correct. Because this is now, this result is independent of theta, the angle between them. So theta could be anything. It doesn't matter, but still this will happen according to this solution. Okay. Let's also understand this geometrically. If you want to understand this geometrically, you can understand it this way, that suppose this is V1 and this is V2. Then the vector parallelogram like this. Now in this parallelogram, we want that the sum and the difference should be perpendicular to each other. That means this diagonal be perpendicular to this diagonal. This is the difference. This is the sum. So the diagonals are perpendicular. It implies that it's a rhombus. It implies that magnitude of V1 is equal to magnitude of V2. This side should be equal to this side. It's independent of theta. So theta could be any value, including obtuse. You can also have this kind of a rhombus. Theta could be an obtuse angle, but as long as this side is equal to this side, that property will still hold. The diagonals are perpendicular. Okay. That's the geometrical solution for this. So you have an algebraic solution as well as a geometrical solution. Shravani, hope this is clear. Now coming back to exercise 4. Next, we will look at question number 3 in exercise 4, C part. So exercise 4, question 3, part C. Let's work this out. So in part C, we have to find out the magnitude of component of A along B. We have to find out the magnitude of the component of a certain vector E, which is along another vector B, or along the direction of the vector B. That's simple. Where E is given to us as 5i cap plus 4j cap minus 6k cap, and the vector B is given to us as minus 2i, 2j, and 3. So minus 2i cap plus 2j cap plus 3. Okay. So this is that kind of situation that suppose this is the vector E and this is the vector B. We have to find this thing as a magnitude. So basically, we have to find the component of A along B. So that is E parallel. It is nothing but E cos theta. So by definition, it is E dot B divided by mod B. Understood? So now next thing what we have to do is we have to find E dot B. So E dot B will become how much? Let's work that out. So 5 into minus 2, so that's minus 10, plus 4 into 2, so that's 8, plus 6 into minus 3, so that's minus 18. Divided by magnitude of B, so that is square root of 4 plus 4 plus 9. So this is becoming how much? Minus 28 plus 8, so that's minus 20 divided by the root of 15. So we could leave the answer this way, or we could write this as whatever. We could leave the answer this way also. Oh, sorry, this root 17 in the denominator. My mistake. Okay. So this becomes the answer. So is it clear, Shikhar? Okay, Rudra, I'll discuss this. Achha, 4D is the same, so these two are clear to you. Now let us move on to next question number 6. Okay, then. Question 6 of this same exercise. Let's go through it all of it. So it says that a vector of magnitude 8 meters. So let us say that vector is B. So B has a magnitude of 8 meters. So when B is added to A, so B plus A, we get a vector which is vector of magnitude 8 meters added to A, which lies along the x-axis. So A is some Ax I cap, let's say. So it lies along the x-axis. So this is a third vector which is along the y-axis and has a magnitude of twice the magnitude of B. So this resultant is lying along the y-axis only. And it's given to you that the magnitude of this is twice of the magnitude of E. So that means Ry is equal to 2 times Ex. So that means we can say that the vector B plus A is equal to 2 times Ex times J cap, or B plus Ex I cap is 2x J cap. So that means the vector B is how much? It is minus Ax I cap plus 2ax, or the magnitude of the vector B is square root of ax square plus, so that is root 5 times ax. So that is the relationship between the magnitudes. So now this is 8. So 8 is equal to root 5 times mod A. Now that's root 5 by 2 times mod R. So from this you can find out mod A and all that. Is it clear? It is given that mod of the resultant is twice the mod of A. नहीं तो see बेटा, Ax is just a scalar quantity ना, तो कितना है उससे थोड़ी मतलब है. See, this means that magnitude of vector A is how much? It is Ax now. So we substitute this here, and this is along the y-axis. So what is magnitude of vector R? It is the y component of R. And what is magnitude of the vector A? It is Ax. Understood? That's all. Okay, so next let's come to the 7th question. Is it clear? Okay. Yeah, Ritika, I will come to question 10. 7th question is like this, that you have a ship which is standing at a point O, sets out to sail to a point B, sorry, A, which is 120 kilometers north of O. Okay, so let's say this is the point from which the ship is supposed to set sail. So then the point E is to the north, which I am taking as my y-axis, and east I am taking as my x-axis. So E is 0,120 kilometers in terms of coordinates. Okay. But because of the unexpected wind, the ship gets blown to a point which is 100 kilometers east of A. So this point B is somewhere over here, 100 kilometers east of. So now we have to just find out this vector. this vector BA, you can see it's in this sort of direction. No? So it has an x component which is along the negative x direction. So its x component is minus 100. It has a y component which is along the positive y direction. It's plus 120. So the vector BA is minus 100 I cap plus 120 J cap in kilometers. And its magnitude okay. So this is the question number 7. Okay, next, let's come to question number 9. Nine and 10 are the next two questions we will do. Okay, so go through question number 9, all of you people. It says A and B are two vectors of magnitude 10 each. If each of them are inclined to the x-axis at 30 and 60, find the resultant of AB in the form of. Okay. So in this question, it should be given to us that AB actually lie in the xy plane. But anyway, because it is given to you in I cap and J cap form only, so there is no K cap. So you have to understand that the question inherently means that this is a two-dimensional vectors problem, not a three-dimensional vectors problem. So this is pretty simple now. They are both of magnitude 10 and they are at an angle of 30 and 60 respectively. So this is the vector E. This angle is 30 degrees. Then the vector B is like this. Also of magnitude 10, but this angle is 60. Now we have to find A plus B in component form. So we have to find E plus B in component form. That is I cap, J cap notation. So for that, first express the vector A and B in I cap, J cap notation. So the vector E is 10 cos 30 I cap plus 10 sin 30 J cap. So the vector E in component form is 5 root 3 I cap plus 5 J cap. Similarly, the vector B is 10 cos 60 as the x component and 10 sin 60 as the y component. So the vector B is 5 I cap plus 5 root 3 J cap. So now you can very easily see here that the sum of A and B will become 5 root 3 plus 5 I cap plus 5 plus 5 root 3 J cap. So you can also express A plus B like this: 5 into root 3 plus 1 I cap plus J cap. This or even this is fine. Okay. Depends on how the answer is expressed in the question. There is a 9th question, people. After this, let's move on to the 10th question. Hope this is clear. Now moving on to the 10th question. So here what is happening? 2 points are given to us in the 10th question. So particle is moving from one point to another. E which has coordinates 2, 1 and B which has coordinates 9, 25. So if suppose a particle is making a displacement from A to B, उसका displacement vector कैसा होगा? It will be this vector. This will be the displacement vector. And if it is making that displacement with uniform velocity, then its velocity vector will also be lying along this. Now it is given to us that the velocity has a magnitude of, how much is it? 50 meters per second. Okay. We want to find the velocity in component form. Okay. So therefore what we have to do here is we have to express the velocity as its magnitude into some unit vector. This is the unit vector. Okay. And this should be along EB. Okay. So in other words, that is along the displacement vector. So that's how you do it. Okay. So you know the magnitude is 50 meters per second. That's given. But what about n cap? N cap you have to find. So n cap will be the unit vector along EB, okay, or along S. So this is the hint to you. Given the coordinates of A and B, you can first find the displacement vector S, and then you can find the unit vector along that displacement vector. So once you get that unit vector, that is your n cap over here. So just multiply the magnitude of V, which is 50 meters per second, with that n cap, and you will get the answer. Okay. So Ritika and others, those who have asked this question, Shekhar, etc., just try this out now. So try it out from the hint which I have given you. So got it now? So first of all, see what will be your displacement vector. Your displacement vector is 9 minus 2 is 7 I cap plus 25 minus 1, that's 24 j cap. So your displacement vector is 7 I cap plus 24 j cap. So therefore, n cap, which is the unit vector along EB or displacement S, that n cap will become vector S divided by magnitude of vector S. So 7 I cap plus 24 j cap divided by square root of 7 square plus 24 square. So that is 7 I cap plus 24 j cap divided by 25, because you know that is equal to square root of 49 plus 5. So that is your n cap. N cap is this. So therefore the velocity vector will become its magnitude multiplied by that same n cap. So 50 meters per second is the magnitude, multiplied by that unit vector is so that becomes, now cancel this with this, so 2, so that becomes 14 I cap plus 48 j cap in meters per second. So that becomes the velocity vector. Okay, so hope this is clear to all of you. Very good, Shekhar. Okay. So now what is pending? Question number 11, right? That's the only question pending. Okay. So next we are going to do question number 11. That's the next question of the same exercise. This was Ritika's question and Rudra's question. So Rudra and Ritika, hope this is clear to all of you. To both of you, that is. Yes, Ritika and Rudra. Okay, good. So now, Shikhar, I think you have asked the 11th question. That's the last one you've asked. So we'll discuss that. Any other questions, please send me, because otherwise I will start with the next chapter after we complete the 11th question. Seventh question in exercise 2. Yes, I will discuss it. So let me complete the 11th question of this exercise 4. Then I'll come back to exercise 2, question number 7. All right, Shikhar. So let's go through the 11th question. It's saying two vectors acting in opposite directions have a resultant of 17. And if they act right angles to each other, the resultant is 25. So calculate the magnitude of the two vectors. Okay. So suppose the two vectors that I'm talking about are acting like this. They're acting in opposite directions. Because this is the vector B. And this is the vector E. So if the angle between them like this is 180 degrees, so you can see that their resultant will actually become the difference of their magnitudes. And that is given to us as 17. Okay. So suppose, assuming that magnitude of E is greater than magnitude of B, we can say that E minus B is 17. That's equation 1. Now suppose I turn the vector B without changing its direct magnitude. I keep the magnitude the same, but I just rotate the vector. Okay, so that is now perpendicular. So the angle is 90 degrees. Now in this case, what will be the resultant? In this case, the resultant will become of magnitude root of a square plus b square, and that is given to us as 25. So that's our second equation. So a square plus b square is 625, and e is equal to 17 plus b. So substitute this here. So we get this equation: 2b square plus 34b plus 17 square, which is how much is 17 square now? 289, right? Is 625. So this equation will become 2b square plus 34b minus of that's given in the question. Beta. Read the question number. It says that if the vectors are perpendicular to each other, then no, it's given anti-parallel. No? Shikhar, read the question. Okay. Opposite directions. In the first part, it is given A and B are in opposite directions. And second part, it is given that they are perpendicular. So anyway, so this becomes yeah. Okay. So you'll reject the negative root and take only the positive root. So minus 7 is rejected because B has to be a positive quantity. And E therefore becomes 17 plus B, 41. So you can see that A minus B is 17, and the root of A square plus B square will actually become 25. No, E will not be 41. E will be E will be 7. Yeah. Okay. So now this you had some other doubt in exercise 2 now, which was that now question number 7. I'm just minimizing this once for all of you to go through. Then we'll come to exercise 2, question number 7. Yeah, so finally A is the smaller one and B is the larger one. So we will have to interchange A and B in the answer. Okay. So we'll have to interchange A and B, and we'll have to make A as the 24 and B as 7. Okay, let's come to exercise 2, question number 7. Finish that off. So that is like this, that just go through the question all of you. It's saying that a situation might be described by two sets of coordinate axes having different orientations. Okay. So let's understand what that means. So suppose I'm talking in 2 dimensions. Suppose my coordinate frame is, or one of the two coordinate frames are considered, is this. Like this. And in this coordinate frame, I'm now considering some vector quantity like this. Suppose this vector is E. So in the xy frame, I would have written the vector E in component form as some EXI cap plus EYJ cap, where if this angle is theta, EX is whatever magnitude into cos theta, and EY is whatever magnitude into sin theta. Now suppose I have a second coordinate frame which is oriented different. So what is meant oriented different? It means that it's in a different kind of, it's making different kind of direction with respect to this. I have a second coordinate frame which is oriented differently. This is what it means. Suppose this second coordinate frame is x cap and y prime, where this angle is some alpha. So that means this angle now becomes theta minus alpha. So this is the vector E in xy system. But similarly, what would be the vector E in x prime y prime frame? It will become E cos theta minus alpha I cap plus E sin theta minus alpha. So in this frame, what is happening? The components are becoming E cos theta minus alpha and E sin theta minus alpha. So if you look at the two frames, you will see that therefore components of the vector E change in the different coordinate frame. But the magnitude of E, that remains same. Also, the direction of E remains the same. The direction of the vector arrow remains same. But it is only the way we have expressed the components they have changed. Where also these unit vectors are different. This is I cap prime and j cap prime, which is along the x prime and the y prime axis. Whereas I and j were along the x axis and the y axis. So this is how we express it in the xy frame. And this is how we express it in the x prime y prime frame. You can see the components are different. These two components are different compared to these two. But the magnitude of the vector is the same. And the way the vector is drawn, the vector arrow is the same. Okay, so that's how you will compare which quantities change and which quantities do not change when we change the orientation of the coordinate frame. Is it clear, Shikhar? Yeah, so now from this, just compare now what the four parts are saying. So for example, so if you consider a scalar quantity does not depend on any axis. It's just a magnitude. So it does not change. But if you consider component of a vector, that is changing. If you consider the vector itself, it is not changing because the vector arrow A will be the same. Okay. And finally, the magnitude of the vector, that will also not change. Okay, so understood this. So with that, all doubts in vectors exercise are clear. Anybody else having any other doubts? Right, people. So I'm assuming with this, your doubts in vectors are all clear, right? Okay, very good. So now let us move on to the next chapter, okay, Newton's laws of motion. So we'll sort of take an introduction into the chapter today, and I will send you the module for Newton's laws of motion also. And you can start reading from the module also about it. Okay. So since we just finished vectors, take a 2-minute break. and just reorient yourself, because after that we will be starting with Newton's laws of motion, which will be our next chapter. So just take a quick 2-minute recess to reorient yourself, and we'll start with a new chapter. Okay, people. So let us begin with Newton's laws of motion. So very important core chapter in mechanics and class 11 syllabus. So this Newton's laws of motion is really describing about the dynamics of motion. By dynamics of motion, it basically relates force, momentum, inertia, etc. These kind of things it relates. So first of all, let's understand the statements, the Newton's laws themselves, written by Sir Isaac Newton way back in 16th century. So as you know, the first of the three laws states the property of inertia. It is called the law of inertia. Whereby every body or any body possesses a property of inertia, because of which what happens that if it is in a state of rest or uniform motion, it wants to continue in that state unless and until acted upon by an external force. So a body in a state of rest or uniform motion has a tendency to continue in its state unless and until acted upon by an external force. Okay. So this tendency to want to continue, I mean, this is not the exact statement in the language of Newton and all, because that is a little bit more cryptic because that's way back in history. So the usage of language, grammar, all that was different. But this is what it means. Okay. So tendency to continue, this is called the property of inertia of a body. So let us understand this with some examples. So for example, if a body is at rest, it will not move until some force is applied. Okay. So this tendency to not move, this is called inertia of rest. This is one example of inertia. It is inertia of rest. I'll give you time to note down, don't worry. Then, for example, if we have a situation where on a frictionless surface, like a very smooth surface of a carom board or something, or the surface of an ice skating rink. So this is a very, very smooth surface. So it's frictionless. Now on this surface, we have a body, like a block or something, which is in a state of motion. So which is moving with a velocity v vector. So this body will continue to move at uniform velocity, okay, until and unless some force is applied. Yeah, that's what I'm explaining. So suppose we have this situation where the body is moving on a frictionless surface. So on a smooth surface, you have a body that is moving with a velocity v. Like you have a smooth surface of a carom board or something. It's almost frictionless, and a body is already moving with a velocity v. It will have a tendency to continue at that uniform velocity v unless it is acted upon by some external force. So that tendency is again the property of inertia. So for example, to stop it, some force should act opposite the velocity. If I want to stop its motion, it's moving at a velocity v like this. So I'll have to apply some force in the direction opposite to the velocity. So that this force will now create an acceleration which will be opposite to the velocity. And then after some time, the body might come to rest. By the time it's here, it might come to rest. Okay. Or for example, to accelerate it further, increase its speed, force should be applied along the velocity vector. So if I want the speed to increase, then I should apply some kind of a force which is along the direction of velocity. Then what I'll see is that after some time, as I'm continuously applying this force, the velocity would have increased to v plus delta, would have increased. Whereas in the earlier example, I've applied force in the opposite direction, so I made it stop. Okay. Or for example, to turn the direction of motion. Force has to be applied. Yeah, I told you, Samarup, I'll give you time to write down. Just let me explain the whole thing first, because otherwise you lose the flow of understanding. I'll explain. Okay, Shikhar, you will understand that question very soon. Okay. But first, just stick for a moment to what I'm saying here. So force has to be applied perpendicular to the velocity for it to turn. So for example, you're taking the top view of this like this. So the block is, this is the surface on which the block is moving. This is the smooth surface. Now along this, the block is already moving with a velocity vector which is like this. Moving with a velocity vector like this. Now imagine it's moving towards the east or something on a horizontal plane, and now I apply a force which is perpendicular to it. I apply a force which is in this sort of direction. So what will happen is this will make the body turn its direction of motion. So from going along a straight line, it will turn like this. And its velocity vector's angle will be changing because of perpendicular force. Because this type of force is called a centripetal force, but we won't get into the details here. But in this case also what is happening, the momentum of the body, which is mass into velocity, is changing. But changing in what manner? Changing in direction. Due to a perpendicular force applied. So its state of uniform motion is changing. So state of uniform motion is changing due to application of force. In the earlier two examples, the magnitude of momentum is changing. So in this example, now the magnitude of the momentum is decreasing due to force F applied opposite. Okay. In this example, the magnitude of momentum is increasing. Okay. So in both these examples, what is happening? The state of uniform motion changes because magnitude of momentum is changing on application of force. Okay. So these examples below are examples of what we call inertia of motion. These are examples of inertia of motion. That is, the momentum P has a tendency to remain uniform until some force acts on the body. Whereas the above example was the inertia of rest. A body which is already at rest will have a tendency to remain at rest until and unless an external force acts. So just start by taking down the key points over here, but more importantly, understanding them, because these are very common examples. You'll find them in all references. Okay, so this property of inertia, let us explore it through these three or four examples. So one is a body which is at rest. It has the type of inertia which is called inertia of rest. That is, it will just simply want to continue in its state of rest until and unless some external force acts on it. If you don't apply any external force, it will just remain in a state of rest. So that is called inertia of rest. Whereas a body which is already in motion, that also has a property of inertia, but that is called inertia of motion. And that property is such that it will have a tendency to continue with uniform motion. That means uniform momentum. Momentum is mass into velocity. So uniform momentum का मतलब क्या है कि velocity का direction भी नहीं change होना चाहिए, magnitude भी नहीं change होना चाहिए. If either direction or magnitude of velocity is changing, or for that matter both are changing, then we'll say that the momentum has changed. So when I say a body has a tendency to continue in uniform motion, it means that it has a tendency to its momentum vector should not change in both direction and magnitude. And to change it, we need to apply external force. So whether we are increasing the magnitude or we are decreasing the magnitude or we are changing the direction of the momentum vector, whichever of the three we are doing, we'll have to apply some force. So that is what the examples below are showing. To decrease the momentum's magnitude, we have to do this. To increase the momentum's magnitude, we have to do this. To change the direction of the momentum vector, we have to do what we are doing in the third example. Okay. So this is showing you the different ways in which the inertia of motion represents itself in a situation, and how to change the rate of change of, how to change the state of uniform motion, we have to apply external force. Whatever way we are changing it, whether we are increasing the magnitude, decreasing the magnitude, or changing the direction of momentum. But according to what we are trying to do in terms of change, we have to apply some kind of external force. So this is the meaning of Newton's first law. Yes. Right, done, Shikhar? Sorry, Somaru. No, Shikhar. Okay. So now make sure you understand these three examples. The inertia of motion examples. In one case, I'm decreasing the momentum by applying the force in the opposite direction. In the other case, I'm increasing the magnitude of momentum by applying the force parallel to the velocity. And then we'll come to the third example again. Okay, so understood the first two examples of inertia of motion. Trying to accelerate or increase the velocity's magnitude, you have to apply the parallel force. Trying to decrease the velocity's magnitude, you have to apply an opposite force. So here, if something is moving along this direction, now to make it turn, be like this, so that its velocity direction turns like this, we have to apply a force, which has to be like this. Continue to turn, you have to keep applying a force which is perpendicular. Yes, exactly, Shikhar. We can turn it by 90 degrees. So, for example, when a car that is moving towards east, it is going on a road like this and it turns like this, and now it's moving towards north. So, during that turn, what has happened is the frictional force acting on the tires continuously it's being acting like this on it, so that its direction changes. You would have heard the term centripetal force in class 9 or something. So that centripetal force is the force which acts perpendicular to the velocity, and that is the type of force which is responsible for changing the direction of motion. Yes, acting towards the center. So while it's turning like this, you can see it's taking an arc kind of shape. So it has a center of curvature somewhere over here as it is turning. So the force is continuously directed towards that center while it's turning. Here, this is some circular arc in its structure. So it will have a center of curvature somewhere over here. Okay, so the main thing is hope the concept is clear over here. Of course, I'll be providing you with the notes, so you don't need to write everything in detail. You just need to understand the three situations I've given you. That to change the magnitude of the momentum or to change the direction of the momentum. And in changing the magnitude, you could either be increasing the speed or decreasing the speed. But in all the three cases, whether you're increasing or decreasing or changing the direction, it will not happen until and unless some external force acts. Okay, so that is the property of inertia of motion of the body. It has a tendency to continue with the uniform velocity. So it has a tendency to continue with constant speed in a fixed direction along a straight line until and unless there is something to change that. And that something to change it is what we call the external force. We'll talk more about force as we go along, but as per Newton's first law, that is the relationship between inertia and force, okay, or momentum and force like that. Now the second law Okay, Somaru. Yeah, so the first law relates the property of inertia, and it relates that the inertia is such that the state of uniform motion will have a tendency to remain unchanged until and unless external force acts. Now, the second law is the one that explains the relationship between force and momentum. So, the statement of the second law, as you know, the correct statement is that the net external force acting on a body equals to the rate of change of its momentum. This is the proper statement of it. So this is called the force law. It relates the property of force. So in mathematical form, this is what it says, that the net force is equal to this quantity. Where I think you have started differentiation in math, so you understand the concept of instantaneous rate of change. Where this symbol stands for the net external force. In other words, that is the sum, a vector sum of all forces acting on the body. So we'll discuss more about this later. And this quantity, this is the instantaneous rate of change of momentum with respect to time. With respect to time. So calculus wise, you understand that this thing is nothing but delta P by delta T, but under the condition that delta T is very small, it's tending to 0. That is instantaneous rate of change or derivative of momentum with respect to time. So this is coming just from the calculus definition, like we've studied in calculus that dy by dx is limit delta x tending to 0 of delta y by delta x. For example, if y is equal to x to the power n, then you know dy by dx becomes nx to the power n minus 1. If y is equal to sine x, you know that dy by dx becomes cos x. So that same meaning it is over here, but instead of y with respect to x, it is momentum with respect to time. So this is the mathematical form of Newton's second law. And this is the one that will be most important for us in terms of problem solving. Okay. All problems of Newton's laws, all numerical applications of Newton's laws will be solved by basically using the second equation in mathematical form, using the second law in mathematical form. So just note down this definition and the meaning of both sides of the equation first. Yeah, Shikhar, rate of change is of two types, instantaneous and average. Rate of change is a more general term, but when we use instantaneous rate of change, we mean it's dy by dx. When we use average rate of change, it just means some delta y by delta x. The delta x need not be a small interval. Okay. So rate of change is more like a general category of operations, but specifically when it is instantaneous, it is called instantaneous rate of change. When it is averaged out over an interval, it is called average rate of change. So instantaneous means rate of change at a particular moment of time. Average means over a certain interval of time. Okay, so finish writing this down, people. Okay. Okay, so of course you should also first of all understand here, add one thing. What is P? P is the instantaneous linear momentum. So P is defined as mass into velocity. This is momentum. That equals mass multiplied by velocity. It's a vector quantity because velocity is a vector and mass is a scalar. We'll talk about the units of both sides of the equation also, but right, finish now. Now let's understand how to deal with the right hand side of the equation, the rate of change of momentum. Yeah, obviously the whole chapter is about applications with examples. So don't worry about that. So momentum being mass into velocity, rate of change of momentum is nothing but rate of change of mass into velocity. Now, when applied to a body of fixed mass, basically what we call any rigid body, then if m is a constant, then you know in differentiation it will come outside and this will become this. Okay. So this is coming from the step that you know that if y is equal to some constant into a function, let's c is a constant, then dy by dx becomes differentiation of the constant into the function. That becomes constant into differentiation of that function. It becomes c into f prime x. Okay. So this is coming from that principle in calculus. So what is derivative of velocity now? By definition, you know that instantaneous rate of change of velocity with time is nothing but the instantaneous acceleration. This is a definition from kinematics. That becomes an instantaneous acceleration. Okay. So we have the relation that net force, which equals to rate of change of momentum, that becomes equal to mass into acceleration, provided mass is constant or fixed. So your Newton's second law gets modified to the more commonly written equation, but this is a conditional statement, okay, for fixed mass bodies. Net force acting on it becomes mass into acceleration. I'll also explain what happens if the mass is variable. Then the equation becomes somewhat different. So what you have to understand is that ये जो equation है, this one, that F is equal to ma, this equation is conditional. It's conditional. And what is the condition? That mass should be constant. Okay. Whereas this equation, that F is dp by dt, that is the universal equation. It's independent of whether mass is constant. So this is a very important point to understand. Now, in this chapter, we will be dealing with situations where the mass is constant. But in a later chapter, we will understand how to apply Newton's second law in situations where mass is variable also. So we'll come to that point. Just note this down first. That dp by dt, or rate of change of momentum, actually becomes mass into acceleration, provided the mass is constant. I'll explain, but I told you there are many situations in which mass is variable. No, nothing moves at speed higher than speed of light. So maximum possible, I mean, nothing can move at the speed of light also. Particles have velocity less than speed of light. That is one of the postulates of the theory of relativity. Okay, so hope you are clear with this. Now moving on. If a body or a system has variable mass, I might say that, okay, how is that possible? So I'll explain to you. For example, the mass of a conveyor belt as material is being added to it. So you have an industrial conveyor belt which is moving along like this, but mass is falling onto it. So its mass is increasing with time. Or you have an example where you have a tanker with a leakage. Okay. So what is happening? Its mass is decreasing with time. Okay. Or you have the concept of rocket propulsion. A rocket going in outer space, it's not affected by gravity. So it is throwing out burning fuel at a very fast rate. So this ejects burning gas at a very high rate. So again, its mass is decreasing with time. So these are all examples of variable mass systems. So for any variable mass system, M is variable with time, with respect to time. So there what will happen is when we look at the rate of change of momentum, that is rate of change of mass into velocity, we'll have to use the differentiation product rule. That is, it will become dm by dt into v plus m into dv by dt. Become like this. So that is equal to dm by dt into v plus instantaneous mass into instantaneous acceleration. So there you can see that net force, which is rate of change of momentum, that will not be equal to mass into acceleration. Okay. Net force will be mass into acceleration plus this additional term dm by dt into velocity. So this will become Newton's second law for variable mass system. Okay, so we are applying the product rule over here of differentiation. Product rule आपने पढ़ा होगा differentiation. Differentiation of u into v is u into dv by dx plus v into du by dx, or it is uv prime plus v prime. So that principle is being applied over here. Got it? So here you are differentiating. You are applying differential on product of two things. So it is differentiation of first into second plus second into differentiation of first. Like that, okay. And since you are asking how it is possible that mass is variable, so these are three everyday examples I am showing you where the mass of a body or a system might be varying with time. It might be increasing or it might be decreasing. Yes, so you can say that when mass is constant, it's just a special case of this thing where dm by dt is 0. You can apply the general definition and just in that you put dm by dt is 0 when mass is constant, and dm by dt is positive when mass is increasing, and dm by dt will be a negative quantity when mass is decreasing. I mean, either way, you understand. Before this, you have written down that. Before this, what was there was f is equal to ma is a conditional statement. Now you come to this, what is happening when it's a variable mass. That depends whether the power has to be increased or the power has to remain constant. But yes, some kind of power has to be applied. Some kind of force has to be applied to keep it moving because its mass is increasing. It depends on at what rate the mass is increasing. If it is increasing at a uniform rate, then uniform power has to be applied to keep the velocity constant. Okay, so like we were discussing, you can treat this like a general equation, and whenever mass is constant, this second term just becomes 0. dm by dt becomes 0, so f becomes equal to ma. Okay, so now in this chapter, however, in Newton's laws of motion chapter, mostly we will always be dealing with situation where mass is constant of a body. The second case of variable mass will come in a different chapter later, where we'll be applying Newton's laws to a variable mass system in a chapter called System of Particles. Okay, so let us conclude this with a simple example to understand the application. So, for example, we now have a block of mass 2 kilograms, initially at rest on a smooth surface, on a smooth floor. Now, I'm showing the top view. That is, you're viewing this from top. So the block is you're seeing the ceiling of the block from above like this, and this is the smooth surface below like this. Now in case 1, what we are doing is we are applying a single force on the block like this. We are applying a force of magnitude, let us say 5 newtons. In case 2, we are applying a combination of 2 forces now. One is acting like this, and the other is acting like this. And it is given to us that the magnitudes of the forces are 4 newtons and 3 newtons. Okay. Again, this is the top view in all these cases. And in another case, now in this case, we are applying the forces in this manner. One force is acting like this, but the other force is acting like this. So they act perpendicularly to each other. So you have to find the acceleration of the body in all the 3 cases. So again, the same magnitudes. Act perpendicular to each other. Find the magnitude of acceleration of the body, which has obviously the mass given to you as 2 kg in each case. So try this out. So what you have to do here is you have to apply Newton's second law, that the net force will become mass into acceleration, because it's a constant mass body. It's a fixed mass body. So this net force will be vector sum of forces. Yeah, so in first case it is just F by M, so it will become 2.5 meters per second square. But in second case, what is happening? The forces are acting in opposite directions. So the net force will have a magnitude of F1 minus F2. So there will be 1 Newton. In the third case, they are acting in perpendicular directions. So F1 plus F2 का magnitude क्या हो जाएगा? Square root of F1 square plus F2 square. Yes, that's correct. Yes, Ritika, that's correct. Somoru, that's correct. No, Shikhar, you have to divide force by mass to get the acceleration. To divide the force by mass. Yeah, Vaishnavi, correct, both the answers. So you have to apply, in each one of these, you have to apply this. Okay. So in case 1, the net force is F only. Okay. So and the action will be in this direction. Same force. In the second case, the net force will be vector sum of F1 plus F2, and the angle between them is 180 degrees. So the magnitude of the net force will become F1 minus F2's mod. So 1 Newton. Okay. So the acceleration's magnitude will be magnitude of net force divided by mass. .5 meters per second. So here also you can see that F1 dominates over F2. So the acceleration will be along F1. This will be the direction of acceleration. But in the third case, what is happening is on the body, the forces are acting perpendicularly. Okay. So in case 3, the forces are acting like this. One force is like this, and another force is like this, and this angle is 90. So you can see that the net force will become like this. So net force is vector sum of F1 plus F2, but here theta is equal to 90 degrees. So that is showing us that the magnitude of the net force becoming square root of F1 square plus F2 square. So the magnitude of the net force is 5 newtons. So the acceleration will have a magnitude of this, okay, again, and the direction of the acceleration will be along this one. So this body will accelerate along this direction. This will be the direction of acceleration. Okay, so hope this is clear, each of the parts. So this is an example of how we apply Newton's second law to fixed mass bodies, and that is typically what we'll do in this chapter. So it is all about vector addition actually, nothing more. All right, people. So that brings us to the conclusion of today's lecture. So I will give you something to read from the module for before the next lecture of Newton's laws, so that you are more familiar with the principles and we can move on to some more tricky type of questions. And of course, we'll start the next lecture with the understanding of Newton's third law, that is the action-reaction principle, and from there on we'll concentrate on the numerical applications. Meanwhile, if whatever is pending in vectors assignments for you people, please complete them this week, including the questions from the test that was concluded last Sunday, the second major test for you people. So in that, any vectors questions you're not able to understand or you're not able to solve, please send me the doubts on WhatsApp. I will help you out with the solutions of that. Okay. So your task this week is to complete anything pending in vectors, and along with that, I will send you some reading stuff from the module for vectors. For Newton's laws of motion. So that's it for today. Honest people.